So today in class you got to do a visual representation of these cross sections that weren't circles. We did squares, equilateral triangles, and semicircles. At least each group got at least to do one of them. What I want to show you right now is how we could actually calculate that volume of that figure that you got. So I want you to think of that mental image of what that picture looked like that you were working with. And we're going to do it all algebraically. So the equation I gave you was a circle, so we can use x squared plus y squared equals 25 since we had a radius of 5. We're going to assume for simplicity's sake for right now that we drew our diameter and we drew those lines perpendicular to the x-axis, because if we're perpendicular to the x-axis, that means we're going to integrate with respect to x, which is something just is a little more familiar to us versus the respect to y. But this problem actually works really nice with either one. So remember that our volume is an accumulation of our areas. I guess it would be nice if I could spell area. And we've got 3 figures to look at. So I'll do a separate video for each figure, but what's nice is once I get through some of the beginnings of it, the rest of it all falls into place quite nicely. Now, the area, of course, is dependent on the figure that you were given. If you were given an equilateral triangle, you're going to have a different formula in here than somebody who had a semicircle versus someone who had a square. So we had squares. I'm going to start with squares first, since those are the easiest ones to do. And we know that the area formula for a square is side squared. So to help us figure this out and actually do this whole accumulation of area, we have to look at our figure. So again, assuming that this is our square with a radius of 5, we know at this point we're at 5, we're at negative 5. If I'm integrating with respect to x, what I have to understand about this figure is I don't want to really look at it in this form. I want to look at it in terms of solving for y. Because if I'm integrating with respect to x, I need to be able to have everything solved for y. So if I take this equation and I solve it for y, I get y squared equals 25 minus x squared. And don't forget, when we square root both sides, we get a plus or minus. And that allows us to get this top part. If we put that into the graphing calculator, this top part is the square root of 25 minus x squared. Whereas the bottom part of this circle happens to be negative square root of 25 minus x squared. So yes, the plus or minus is important and we do need it. Now when we did our squares and we cut them out and we measured, we had to measure them in relationship to the length from here to here. That was perpendicular to that x-axis, or in our case was our diameter. So what controlled the side of our square was this length. And as I get closer to the edge of the circle, we know that the side of the square got smaller. And as we got closer and closer to the diameter, we know that the sides of the, boy, I am so not perpendicular, the sides of the square got bigger, which of course the one that went right through the diameter should have been your tallest square. So keeping that in mind, that this is what's changing, is the length of your side, what's controlling that? And it happens to be the function. So this top curve minus your bottom curve, boy, this should sound familiar, is actually controlling, in this case, the side length of our square. So to find S itself, it would be the top curve minus the bottom curve. A little bit of quick algebra, that becomes 2 square roots of 25 minus x squared. So if I want to find the length of any side of the square that I created, it's coming from this formula right here. Now if we know this, to calculate the volume now actually becomes relatively easy. So the area formula for a square is side squared. We know side. So to find the volume of a figure with cross sections that are squared, We're integrating again with respect to x. We're going from -5 to 5. I'm going to put the formula for the area of a square in here. And the formula for the area of a square is your side squared. So that's really the only difference between what we were doing before and what we're doing now, is instead of putting in the area formula for a circle, we're putting in the area formula for the shape that we are trying to find. Of course, making sure we know, how do I find the length of this particular side or figure that I'm using? So from here, it's nice when I square it. Don't forget to square the 2. That becomes 4. The square root disappears. And at this point in time right now, I could go right to my Math 9 key. If I want to do just a little bit more work to simplify that, I can. If I want to show off my antiderivative skills and such. So again, your calculator can handle the rest of this. If you wanted to practice integration, perfect. So this becomes 25x minus x cubed over 3. You're evaluating it from -5 to 5. And I just threw it in my calculator, and provided I did it correctly, you can double check me. I think my volume then of that figure would be about 18.667. So nothing magic and mysterious. The tough part of this is kind of figuring out, are we perpendicular to x or y? So am I integrating with respect to x or y? And then what is controlling how large or small my figures are? And in this case, the side lengths were controlled by the top curve minus the bottom curve. So I'm going to do another video with equilateral triangles, and you'll see how we can use all of this information. It's just going to change a little bit right here.